For the introduction, first I will introduce the working principle of a valve. A valve is a mechanical device used to start, stop, and regulate the flow of fluid, such as liquids, gases, or steam in a system. It controls the fluid flow by changing the internal flow area inside the valve. In operation, when the valve is open, the fluid flows with low resistance. When it is partially closed, the flow rate, velocity, and pressure will change. And when the valve is fully closed, the fluid flow is completely blocked. The behavior of valves follows fluid dynamics principles such as continuity equations and Bernoulli equations. In addition, temperature and pressure can also affect the properties of the fluid and the performance of the valve. Valves are widely used in many industries such as oil and gas, petrochemical processing, refrigeration system, natural gas transportation, and power plants. They are important for controlling flow, preventing backflow, and ensuring pressure safety in industrial system. Next are the objectives of this study. The first objective of this study is to explain the working principle of the assigned valve device. And the second one is to determine and graph the relationship between multiple input and output parameters that affect the performance and effectiveness of the device.
Assalamualaikum warahmatullahi wabarakatuh. My name is Azain Azhar. I will explain a theoretical calculation for our valve. To understand how our valve performs, we start with the core physics, that is Bernoulli equation. You can think this as the squeeze effect. When the valve is partially closed, the flow area narrows, forcing the fluid to speed up. Bernoulli tells us that the speed increase, the pressure must drop. This relationship is exactly how the valve regulates flow by converting pressure into kinetic energy. Now, how do we turn the concept into precise data? We move into our mathematical formulation. We don't just guess the behavior. We will use two laws of nature shown here. That is the first one, the continuity equation, which ensures every drop of water entering the valve is accounted for at the exit. Second one, the momentum equation, which tracks the physical force, gravity, and energy losses as the water moves through the valve geometry. Because real-world flow isn't always smooth, we use simple algorithms to balance the pressure and velocity steps. More importantly, we apply the RNG K epsilon model. This is the industry standard for predicting the complex swirl or vortices created inside the valve, ensuring our simulation stay efficient but highly accurate. The bottom line is the validation. We compare this mathematical prediction against our actual experimental data. This result was an error margin of less than 2%. This confirms that our theoretical model is near perfect match for how the valve function in reality. So next, we move to methodology. Our methodology follows a dual-phase approach, integrating physical experimentation with high-fidelity numerical simulation. So first, we compare a standard 65mm metal gate valve against a modified version featuring a rubber sleeve with an elastic modulus of 0.1 GPa. The setup used a recirculation pipeline with a constant 1.83 meter head and acrylic pipes to ensure the flow was fully developed. We record discharge data at 90 degrees interval for over 13 full wheel rotation about 46,800 radians. By allowing 5 minutes for the system to reach a steady state after each adjustment, we achieve a high accuracy rate with an error margin of less than 2% compared to theoretical models. For the numerical phase, we utilize a NSYS fluid with pressure-based steady-state solver. We select the transition turbulence model specifically for its ability to accurately predict boundary layer transition and flow separation. After a grid sensitivity analysis of 6 different measures, we identify grid 5 consisting of over 831,000 elements as the optimal configuration. Finally, we perform simulation using both water and SAE 15W14 oil. This allows us to evaluate how different fluid viscosity impact pressure gradients and the dampening effectiveness of the modified valve. This comprehensive approach ensures our results were both physically validated and numerically robust.
So for simulation results, for valve efficiency, the more efficient the valve, the more we can minimize energy loss during the transfer of fluid systems and giving the valve a better performance and more cost saving. Also, it reduces losses and enhance system performances, promoting sustainability all in a way to promote the greener environment.
Hello, my name is Iskandar Zulkarnain and I will explain about the analysis of results. First, in terms of efficiency, the modified valve with the rubber sleeve shows a clear improvement in flow stability compared to the standard valve, which experienced significant discharge fluctuations due to flow separation. The rubber sleeve helps reduce turbulence and pressure oscillations, and as a result, the discharge becomes smoother and more consistent. In addition, the accuracy of flow measurement is improved. The system achieves about 12% discharge fluctuation and less than 2% error compared to theoretical values, indicating good reliability for practical applications. The modified design also provides better mechanical control, where the flow rate is more directly related to valve rotation, reducing instability such as the hunting effect. However, there are several limitations to consider. The analysis is based on a steady-state simulation, so transient effects like water hammer and sudden pressure changes are not captured. The model also assumes constant temperature, whereas in real systems, temperature changes can affect fluid properties like viscosity and density. Furthermore, the simulation uses idealized geometry, meaning that factors such as surface roughness, wear, and leakage are not included, which may lead to higher losses in real applications. And lastly, the oil is modeled as Newtonian fluid, although it may behave differently under certain conditions. Overall, the modified gate valve demonstrates improved efficiency and stability, but these limitations should be considered when applying the results to real-world situations.
Assalamualaikum. So now I will briefly explain how a valve works and where it is used. So first, what does a valve do? Its basic function is to start, stop or control the flow of a liquid or gas. It controls flow by changing the size of the opening inside. And when the valve is open, the fluid flows freely. When it is partially open, flow slows down and pressure drops. And when it is closed, flow will stop completely. So the key principle here is Bernoulli's effect. So basically, when the fluid passes through a narrow opening, it speeds up, and faster speed means lower pressure. This pressure change is what allows the valve to control the flow. Valves can be operated manually by hand or automatically by a machine or a sensor. So now, where are valves used? Valves are found in many places in water supply system. They turn water on and off in homes. In oil and gas pipelines, they control flow under high pressure. Meanwhile, in power plants, they manage steam to generate electricity. And in factories, they regulate chemicals and gases. And in HVAC systems, they control heating and cooling in buildings. For an everyday example, think of a kitchen faucet. It is a simple valve. Turn the handle, water flows. Close it, water stops. Another example is a water heater. It has a pressure relief valve that opens automatically if pressure gets too high. This prevents the tank from bursting. So in short, valves are everywhere and they work by controlling flow through pressure changes. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Islam. So I will explain about 3 input for an effective valve and 3 input that make the valve ineffective. So the first one is 3 input for an effective valve. Incorporation of a rubber sleeve, the modified gate use a rubber sleeve to minimize turbulence and suppress the formation of separation zones. This acts as a structural dampener that ensures a stable discharge profile. Second one is optimize mechanical parameters. It for adjusting design factors such as valve lift and spring stiffness reduces resistance loss and lowers impact stress on internal component. Uh, the last one is precise internal geometry. It used to optimize piping geometry such as inclusion of a pipe bend significantly improve measurement accuracy and reduce discharge fluctuation to 12%. So we move to the next one is three input that make a valve ineffective. Formation of separation zone in standard gate valve, fluid often detached from the valve surface, creating high energy separation zone that lead to self-discharge fluctuation. Second one is improper valve dynamic. Inefficient timing or motion of the valve can lead to reverse flow and increase impact speed. The valve plate also with oscillation, which cause premature wear and fatigue damage. The last one is extreme pressure difference. In a standard configuration, increase the pressure difference leads to a decreasing discharge trend characterized by extreme fluctuation due to internal turbulence.
Hi, my name is Muhammad Akid Zambi Mahimi, and today I will briefly explain what outputs make the valve effective and ineffective. Firstly, we will look at what outputs make the valve effective. The first characteristic is stable and linear discharge pattern, which is the result of modified gates valve equipped with a rubber sleeve that ensure the consistent, smooth, and linear relationship between the valve rotations and flow rate. This linear discharge allow minimal fluctuations across the rotation angle. Next, the dampening of pressure oscillations. The rubber sleeve act as a structure dampener, suppressing pressure fluctuations and maintaining a steady discharge rate. It leads to a steady flow and better control. Thirdly, it provides high measurement accuracy. The low error, which is below 2% between the experimental and theoretical values, these high precisions make the device effective not only as a flow regulator but also as a reliable flow meter. Now, let's look at what outputs make the valve ineffective. First and foremost, the formations of separation zones and turbulence. The separation zones cause severe turbulence and discharge fluctuations, leading to unstable flow readings and poor control over the fluids. Secondly, the high energy loss due to turbulence. When low viscosity fluid like water travels at high velocity, they could become a turbulence flow as a water eddy viscosity rose sharply and led to higher energy loss, overall reducing the efficiency. Lastly, the unstable discharge with flow direction sensitivity. Extreme, extreme fluctuations in discharge between clockwise and anti-clockwise rotations as pressure difference increase. This inconsistency this inconsistency indicates poor mechanical regulations, making the valve unreliable for control applications.